picking up good vibrations.
In this short video, we'll talk about the Fourier transform. We start by deriving the formula for the Fourier transform of a given signal, and this will have as the starting point the Fourier series formula. And then we'll ask ourselves if, given the Fourier transform, we can recover the original signal, and that's through the inverse Fourier transform formula. Now, as a motivation, we have seen how to represent periodic signals as a sum of sines and cosines and a constant term. And what about periodic signals? Can we represent them in a special form as well? Let us start with signals that have a bounded support. That means that they are zero outside of a bounded interval. The idea here will be to consider a periodic replication of the signal of interest denoted by x, and the periodic replication will be denoted by x tilde. We'll represent this periodic replication x tilde by a Fourier series, and we'll let the period go to infinity and see what happens to the Fourier series coefficients. Say, for example, for this rectangular wave, we can simply pick a sufficiently large period capital T and periodically replicate the rectangular signal around capital T times 2, minus capital T times 2. And then we let capital T go to infinity, and we see what happens to the Fourier coefficients of the periodic replication of x tilde. This is the plan for now. And as an example, suppose that we use the formula we derived previously when we talked about the Fourier coefficients of the square wave. If you remember, these Fourier coefficients ak were real because the function is even. Now, we can notice in the formula for these coefficients that the dependency in the numerator inside the sine function and in the denominator is quite similar. Actually, if we multiply both the numerator and the denominator by 2 pi over capital T, it becomes even more similar. And if we call 2 pi over capital T k, if we call that omega, so omega equals 2 pi over capital T k, we then obtain that the coefficients are given like this. Can be obtained, the AKs can be obtained by evaluating this function 2 sine of omega capital T1 over omega at time points 2 pi over capital T k, and then we still need to divide it by capital T. Now, you can see here in this figure that if indeed we plot this envelope function 2 sine of omega T1 over omega, and we multiply by capital T, the coefficients, when we multiply them by capital T, are really the samples of this envelope function. So let us see if this works for a general signal x of t. We start by defining this function of omega x of j omega, which we call the envelope. And this is defined as the integral from minus capital T over 2 until capital T over 2 of the signal x of t. But since the signal is assumed to have a bounded support, we can actually take the integral from minus infinity until infinity. And that's how we define this envelope x of j omega. So the formula is the integral from minus infinity to infinity of x of t e to the power minus j omega t. This function has a strange notation, x of j omega, but do not worry about this for now. Just think it's capital X of omega, and it's a function of omega. Now, this function will be an envelope. And why? Because if we define x of tilde to be the periodic replication of x, and if we evaluate the Fourier coefficients of x of tilde, we will get that they are obtained by evaluating this function when omega is replaced by 2 pi over capital T k, and then dividing by capital T, just as in the example that we've seen. And this is a general property. How can we conclude this? We evaluate the Fourier coefficients of x tilde. That is, we take this integral here over a period, and since the functions x and x tilde coincide over that period, we can now replace x tilde by x in the integral. Now that we have done so, we can change the boundaries, the limits of the integration, since x, not x tilde, but x is 0 outside of this integral between minus capital T over 2 until capital T over 2. And we get this function x of j omega evaluated at omega, when omega equals 2 pi over capital T k. Now, this x of j omega is in fact the Fourier transform. Now, conceptually, we can recover the signal x of t from this Fourier transform, from this envelope function capital X. And why? We can follow the following procedure. We can sample this function x of j omega at times 2 pi over capital T k. We sample it. We see those samples as we still have to divide by capital T, but we see those samples, ak, as Fourier coefficients of a periodic function. We plot that periodic function, and then we extract the signal x of t. But can we find a general formula to do this, from the Fourier transform to get the original signal x of t? Yes, we can, and the expression is given here. It's 1 over 2 pi, the integral from minus infinity until infinity of x j omega e to the power of j omega t d omega. Here's the technical justification. We can write the expression that we had for the periodic replication of x tilde as the summation from k equals minus infinity plus infinity of ak e to the power of j k omega naught t, but ak's are nothing more than 1 over capital T of x of jk omega naught. Now, we know that capital T is nothing more than 2 pi over omega naught, so we can write it also equivalently as shown here. Now, we can see, since capital T will go to infinity, omega naught will go to 0, and this new summation that we have is nothing more than an approximation to the integral that you see for the expression for the inverse Fourier transform. So the inverse Fourier transform allows you to recover the original signal from the Fourier transform, and this is the formula that you get. This formula is also valid for signals with unbounded support. Now, as a summary, given a signal x of t, we can take the Fourier transform by taking the integral from minus infinity to infinity of the signal x of t e to the power of minus j omega t. And there's a one-to-one transformation between capital X and x of t. We can get back the signal from this Fourier transform by computing 1 over 2 pi, the integral from minus infinity to infinity of capital X j omega e to the power of j omega t. This is called the inverse Fourier transform. This is the bijection under mild assumption for large class of signals x of t. Now, t is often referred as time, and omega is often referred as frequency. The interpretation for this formula is that we can write also an aperiodic signal as a sum, in this case actually an integral, of these exponential functions e to the power of j omega t.